I will continue our discussion for the second part of chapter 10. And now the last thing we were talking about, which was the halogenation of allylic position or halogenation of alkenes. In principle, whenever we have alkene, we allow it to react with NBS. NBS is very selective for halogenation of allylic position. Again, what's the NBS? The NBS is N-bromosuccinamide. This is the structure of it. This is called NBS. When we allow it to react with NBS, what we are going to get selectively, we are going to get halogenation of, or bromination specifically, at allylic position, always. The allylic position, what's going to be brominated, either this one or this position, because as we have explained in the previous chapter, in the previous lecture, we said this allylic position, the allylic intermediate is the most stable radical, and therefore the reaction will lead to the formation of allyl bromide. Allyl bromide. You follow me? Now regarding the mechanism, we are going to skip the mechanism due to the time limitation. I'm just going to show you the final comparison of the stability of the radicals. As we said, allylic radicals, CH2 double bond CH2 radical is more stable than or equally stable to let's say tertiary radical, and the tertiary radical is more stable than secondary, and the secondary is more stable than primary, and the primary is more stable than the methyl, and the methyl is way much more stable than the vinylic. So this is simply the overall relative stability of the radicals, as you can see. So we will have, this is simply, as we said, the allylic radical is the most stable, then or most stability tertiary, then secondary, then primary, methyl, and then vinylic. So this is allyl radical, this is tertiary, as you know, and this is secondary, and this is primary, this is methyl, and this is vinyl radical. So this is the overall stability of radicals. Now, if we now take in this allyl halide and we allow it to react further with KOH and with some heat, what we are going to get, elimination reaction. Actually, we will discuss this in more details in the next chapter. Elimination, we are going to get elimination of HBr. So there will be elimination of HBr molecule where we have this halogen and removal of the adjacent hydrogen. So at the end of the day, we are going to get a 1,3-cyclohexadiene. So this is simply what we are going to get, which is simply 1,3-cyclohexadiene. That's the major product what we are going to get if we continue. If we allow the allyl bromide to react further with KOH with a bit of heat, what we are going to get elimination reaction, and the final product will be 1,3-cyclohexadiene. Clear so far, guys? Is there any questions so far? Hello?
Victor, can you please repeat the last thing?
Yeah, it's just, as I said, if we take this allyl halide and we react it with KOH and heat, these reagents, generally speaking, the KOH and heat, it makes elimination. Elimination, as we explained, it's simply a removal of a neutral molecule from the compound, the reactant. In this case, we will have elimination of HBr. So one halogen from here, I'm just going to show it to you with different colors. So one halogen from here, the halogen which was already, and the adjacent hydrogen in here. So the removal of these two species will simply leave a double bond in here, and therefore we are going to get 1,3-cyclohexadiene. Do you follow me? And that's why actually if I asked you to start from cyclohexane, how can you prepare? If I asked you, show starting from cyclohexene, let me just write this, the question specifically. Starting from cyclohexane and using, this is a typical synthesis question, and using any other inorganic reagent if needed, show how can prepare the product. So this is a typical, as I said, a typical synthesis formula of a question. So always starting from certain reactant and using any other inorganic reagent, which means you are free to use any other inorganic reagent, if needed, of course, whenever you need it. Show how could you make the synthesis. Generally speaking, this the answer of this question is either could be one step, could be two steps, could be three steps, and so on and so forth. So you should think of. Now, as you can see, this is here 1,3-cyclohexadiene. The only method to prepare cyclohexadiene or 1,3-diene, it's simply by starting from allyl bromide. The allyl bromide, we can always prepare it from the corresponding alkene. So in other words, you should think in a retrosynthetic way this way. So this here can be prepared from the corresponding allyl bromide. So if we have allyl bromide like this, we can, by allowing it to react with KOH presence or sodium hydroxide in presence of a little bit of heat, we can get it. Now, the allyl bromide, as we have explained in this lecture and the previous one, the only method to prepare allyl bromide starting from the corresponding alkene and reacting it with LBS. Now the question is how to start. Where was the question? Actually the question is starting from cyclohexane here, as you can see. So starting from cyclohexane, we need to prepare that product. You follow me? So we are just following it in a reverse method. Now, the question is how to prepare the corresponding alkene. The corresponding alkene, it can be prepared again by elimination if we have alkyl halide. So if we can introduce a bromide here, for example, by KOH again with heat, we can get the final, the alkene. Now, how can we introduce a halogen to alkane? The only method which we have explained in the previous chapters when we studied the alkane and the chemistry of the alkane, we said we can make halogenation by Br2 in presence of HU, for example. So as you can see, this conversion requires how many steps? 1, 2, 3, 4. 4 steps until we reach the final product. Again, whenever you start, whenever you want to start from, just a second, let me finish. Whenever you want to start from saturated alkane, the only reaction available for you is just halogenation. So you just do halogenation. So you can introduce the halogen. Secondly, then this halogen, as you can see here, we can eliminate it. We can make a double bond and to form it to alkene. Then we can introduce selectively, we can introduce the halogen at the allylic position, and this is the allylic position as we said, by NBS. So we introduced it. Then again, we can make further elimination between this halogen and then near the adjacent hydrogen, and then we end up with 1,3-cyclohexadiene. Yes, your question. Your question. Hello?
It's clear now.
Clear? Sure? Okay. All right. Now, let me now say or move to another section, which is the preparation. What are preparation or preparative methods for alkyl halides? How or from which functional groups we can prepare alkyl halides? Or preparation of alkyl halides. Generally speaking, alkyl halides can be prepared. The first method is from alcohol. So whenever we have alcohol, we can simply convert the carbon attached to OH to carbon attached to the halogen by reacting with hydrogen halide. For example, if we have ROH, where here we have an alcohol. Now we can, by reacting with HX, we can convert it into the corresponding RX, which is in this case the alkyl halide. Do you follow me? So here, as you can see, the alcohol, the OH which was attached to the carbon, will be replaced by a halogen by reacting with the corresponding hydrogen halide. Where here, if you want to introduce, for example, a BR, then for sure you should use HBr. If you want to introduce, if we allow to react with HBr, then we are going to get here a BR. If you allow to react with HCl, then you are going to get in here a Cl. If you allow to react with HF, then you are going to get HF. Most likely we are not going to use HF, but what we mean here, it's for example HI, here you are going to get I. So these are this is the first method of preparation of alkyl halides. Now, the weakness or simply the disadvantage of this method that there is a variation of the rate of the reaction. In other words, this reaction is good for certain type of alkyl halides. So the ease of reaction, or let's say the rate of reaction simply will be tertiary alkyl halide faster than secondary and tertiary alcohol faster in reaction than secondary, faster in reaction than a primary. So that's the point in here. And therefore, this reaction is mainly good for the preparation of tertiary alkyl halide. That's actually the limitation of this reaction, what we can say. So it's good enough to prepare tertiary alkyl halide if we want to prepare tertiary alkyl halide. If we want to prepare primary or secondary alkyl halide, we will talk or we will need to use the next methods which we are going to discuss after this slide. You follow me? So, for example, if we want to prepare, or if we want to convert, for example here, CH3C, CH3, CH3OH, this tertiary alcohol to the corresponding bromine, we can use by HBr, we can convert it easily to the corresponding bromine or tertiary bromine. So this reaction goes nicely. But with a primary or secondary, then it's not good method because we may need harsher conditions, or we may need, or we may get or end up with more byproducts. So let us just make the story shorter. This method is optimum, let's say, for tertiary alkyl halides. Is that fine, guys? Is that clear? So this method will be good enough, will be optimum for the preparation of tertiary alkyl halides. If you want to prepare secondary or primary, as I said, we will discuss it in the next slide. Clear so far? Is that quite clear, guys?
Yes, doctor.
Okay, so this is the first method. The second method for the preparation of alkyl halides, which is simply by reacting with thionyl chloride or phosphorus tribromide. So the second method and the third method are good enough. The second method, which is simply by reacting the corresponding alcohol with thionyl chloride. This is called thionyl chloride, SOCl2. And the structure is simply S-O-Cl, thionyl chloride. If we allow the thionyl chloride to react with the alcohol, and mainly if we're talking about primary or secondary, then we're going to get RCl. So we can introduce a chlorine atom or a chloro substituent to the alkyl by reacting the corresponding primary or secondary alcohol with the thionyl chloride. Do you follow me? Or if we want to introduce a bromide, then we need to react the same. The third method will be reacting the primary or secondary alcohol with phosphorus tribromide, PBr3. Then what we are going to get is bromo alkane. Do you follow me? So these two methods, method number 2 and number 3, these methods are optimum for preparation of primary or secondary alkyl halides. Do you follow me? These are the three methods, as I said, and to make the story short, we have three methods for the preparation of alkyl halides. The first method, which is good and optimum for the preparation of tertiary alkyl halides, which is the reaction of tertiary alcohol with the corresponding hydrogen halide. The second method, which is good for primary or secondary, which is introducing a chlorine by reacting the corresponding primary or secondary alcohol with the thionyl chloride. And the third method, which is again good for primary or secondary alcohol by reacting primary or secondary alcohol with the phosphorus tribromide, we will introduce a bromine to the alkane. And in this case, we have three methods for the preparation of alkyl halides. Any questions so far? Is there any question? Alright, now let's move to a new topic in here in this chapter, which is the Grignard reagents and Grignard reactions. And this is, by the way, is one of the very important aspects of organic chemistry. Just this board is making me crazy. It moves. I think I should stop it from movement. Anyway, I'll talk about it later. Grignard reagents. We have a very famous reaction. If we take any alkyl halide, Rx, where X here is any halogen, like for example chlor or brom or iodine. And the R here, it can be anything. It can be sp2, can be sp3, can be vinyl, can be aromatic, can be aliphatic, can be vinylic, can be any R group, any in general, any alkyl halides It can be primary, can be secondary, can be tertiary. There's no limitation for this reaction. Any alkyl halide, any halogen attached to any carbon, it can be converted to this new reagent by reacting first with magnesium in the presence of dry ether. We are going to convert it into R. Let me just write it again here. RMgX. You follow me? So here, if we take specific example, if we take, for example, bromobenzene, and we allow it to react with magnesium in the presence of ether, we are going to get this Grignard reagent, MgBr. If we have, for example, CH2 double bond CH, Cl, and then we allow it to react with magnesium in presence of ether, we're going to get phenolic Grignard reagent. If we take, for example, any example, let's see here, for example, tertiary alkyl halide, for example, CH3, C, CH3, CH3, IUT, and then we allow it to react with magnesium, presence of dry ether. What we're going to get, we are going to get the corresponding Grignard reagent. Do you follow me? So this is a very wide scope and broad scope reaction. So there is no limitations. Any alkyl halide can react with magnesium in the presence of ether or THF. Both are inert solvent, and they should be both dry solvent in order to make the reaction take place or make the reaction happen. So what's the beauty of this reaction? What's so important? What's so special about this reagent? This is called, again, Grignard reagent. So what's so special about this reagent? Now, so special about this reagent is what we call it the reverse polarity. This is a very special type of organic compounds where we have the polarity is unnatural. So the natural polarity of carbons in its organic compounds, that the carbon should carry a partial positive, because most likely in most of the cases carbon is connected to more electronegative atoms such as oxygen, nitrogen, sulfur, halogen, whatever. So that's why most of the time the carbon carry a partial positive. But when the carbon here, where we have here carbon, wherever the carbon is, when the carbon here is attached to magnesium, what would be the polarity? What would be the partial charge on the carbon if it is attached to a metal like magnesium? What do you think? What should it be?
Minus.
Exactly. It's part, but of course we call it partial minus. So in this case, as you can see here, in this case, this is the example where we have the carbon as a nucleophile. So the behavior of the carbon will behave as a nucleophile because simply it carries a partial negative or a negative charge in this case. Do you follow me? So that's actually what's so special about this reaction. So you will actually study this reaction in more details in the organic 2 later on in the next semester if you continue studying organic chemistry. And a very important chapters will be reactions of Grignard with carbonyl containing compounds. Later on you will study it, but of course you should imagine and you should think of the behavior of the Grignard. It should be all of the time will behave as a nucleophile, and it's powerful nucleophile. It's powerful nucleophile. Now at the same time, it has another behavior. The Grignard here, it has or it can be considered as powerful base. Do you follow me? It is a very strong, and powerful means, of course, as you know, very, very powerful, strong base. Do you follow me? So which means this reagent, in the presence of any traces or any slight acidic hydrogen, it will decompose. In other words, if we have H plus, wherever this H plus coming from, as I will explain it to you, what we are going to get, RH plus, magnesium oxides or whatever, or hydroxide and so on. Anyway, what's important in here is that, just I want you to focus on this, that we can decompose this Grignard reagent by reacting with acidic hydrogens. And therefore, actually, that's why in order to be able to prepare such a reagent, we need to be sure or to make sure that the reaction conditions are very dry. And that's why we always highlight the importance of the use of dry ether or dry THF. So the solvent where we are going to do the reaction must be completely and 100% dry in order to be able to keep this. Because if the reagent or the reaction conditions was not dry, then the reaction, the Grignard will not survive and it will simply be decomposing to the corresponding alkane. Do you follow me? So, in principle, the Grignard will decompose. Let's say here, Grignard reagent will decompose in presence of these functional groups, ROH, for example, any acidic hydrogen. This here, for example, ROH, I'm just going to use another color. RSH, RNH, RCOOH, of course. RC111CH. All of these functional groups are acidic enough, which will simply decompose the Grignard reagent and will convert it to the corresponding alkane. So we should avoid these reagents in principle. Now, for example, this is actually this method. Keep this in mind, and let me ask you this. Starting from, let's say, cyclohexane, for example, or cyclopentane now, show how could you prepare such a product. And where D here, some of you may ask, what's the D? What's the D here? D represents or stands for what? When we say D in chemistry, stands for what? Any answer?
Highlight.
No, it's a deuterium. Deuterium, it's isotope of hydrogen. It's an isotope of hydrogen atom, which is called deuterium. Deuterium, we call it. So it's like hydrogen, but it's just isotope. So what's the isotope? What's the isotope actually in chemistry? It's same atom, has same atomic number, but different what? Mass number. You follow me? So the difference between hydrogen and deuterium, that the hydrogen we specified as 1,1, but here we specified as 1,2, where here always the lower number is atomic number while the higher number here, the above number here, we'll call it mass number. Do you follow me? So deuterium and hydrogens are just isotopes of each other. So anyway, how to do or to accomplish such a conversion or such a synthesis or such a preparation, we need to think in a logical way in a reverse manner. So we start up with the product. So the product here is like we want to specify or we want to introduce the hydrogen. The hydrogen here to be attached to the carbon, that means the carbon should be carrying a negative charge. And the only way to carry a negative charge, it's simply if we have, for example, the Grignard reagent, as we said, because this is the only example of organic chemistry where we have the carbon carrying a negative charge, because as we said, due to the low electronegativity of the metals in general and the magnesium in principle and specified issue. You follow me? So if we allow this to react with D2O, which is simply, again, it's like, coming from H2O, but it just, instead of having hydrogens, here we will have a deuterium as the isotope. Now, how to prepare any Grignard? Any Grignard can be prepared from the corresponding alkyl halide when reacting with magnesium in the presence of ether or THF. Then, again here, how to introduce a halogen to alkane? The only possible way to do so is simply by reacting with bromine in presence of heat, for example. So as you can see here, we can do such a conversion by like 1, 2, 3. 3 steps we can do this conversion, like introducing specifically an isotope of the hydrogen on the alkane system. Is there any question so far? Is there any question? All right. Yes. Yes?
It is clear.
Okay, perfect. Now let's move to another section, which is the organolithium compounds. Organolithium compounds. Organolithium compounds. In principle, this is the whole issue here. It's a general title in the organic chemistry, which we call it organometallic compounds. I think it's very obvious from the name what's the meaning of it. Organometallic, what does that mean? It's simply we are dealing with the chemistry of the compounds where we have a metal, which we represented or abbreviated by M, attached to or connected to by a covalent bond to a carbon, regardless what this carbon is. This type of, this class of compounds, we call it organometallic compounds. When we specify it like organolithium, that means it's very simple, like carbon attached to a lithium. Carbon attached to a lithium or organolithium compounds, whatever we studied for the Grignard, it's exactly going the same way, nothing different. Just except that instead of the use of magnesium metal, we will use lithium metal. So in this case, Rx, again here, regardless of the R, regardless of the X. So any R, any X, when we allow it to react with lithium instead of magnesium, in the presence of dry ether or THF, either which, again, it's just a solvent. You follow me? What we are going to get, R lithium. That's it. Whatever we said about the Grignard here, just the difference is the Grignard will be like, it was like RMGX, because simply the magnesium is in the second group, but the lithium is in the first group. So that's actually the only difference. So this is the Grignard, and this is the organolithium. You follow me? Now, the same, whatever we said here, it applies there. In other words, again, the organolithium is a nucleophile because simply the polarization of this bond will be partial negative, partial positive, or plus minus. In this case, the R here, whatever the R here, when it is attached or connected to the lithium, will be a nucleophile or will behave as a nucleophile in this case. Do you follow me? Now, in this case here, we have actually the R lithium here. We can use it for the preparation of a new reagent, which we call it Gilman reagent. But before that, is there any question about the organolithium compounds and their preparation? Gilman reagent now. Is there any question so far? Waiting your reply. Is there any question so far?
No, doctor.
Okay. Now, for what we need the organolithium, or one use of the organolithium actually, what we can use it, we can take the R lithium here and we can allow it to react with cuprous iodide or cuprous iodide, right? And then what we are going to get, a new organometallic compound, which is simply R2 attached to copper and then attached to lithium. This reagent here, we call it Gilman reagent. You follow me? Now again, similarly, any organometallic compounds will be always, the polarization of the bond will be partial negative, partial positive. That goes without saying. Do you follow me? But why we need it? Why we need this Gilman reagent? Because Gilman reagent has the ability to react with any other alkyl halide. The Gilman reagent has the ability, so as you can see, R2 copper lithium can react with Rx, where X here is any halide, is any halogen, and R is any alkyl. Now, what we can get here is R compound. Let's just differentiate this R with this R. Let's call this R prime. So we are going to get R prime. In other words, this reaction is extremely important in what we call it elongation of the chain. Elongation of the carbon skeleton. As you can see here, we may start with a certain number of compounds. We will end up with another one. Do you follow me? Let's take specific example and see. For example, if we have, for example, methyl chloride, suppose, methyl chloride. We allow it to react with lithium in the presence of ether. What we are going to get first, we are going to get methyl lithium. If we allow the methyl lithium now to react with cuprous iodide, copper iodide, what we are going to get, the Gilman reagent, which is CH3 by 2 copper lithium. This is the Gilman reagent. Now, if we allow now the Gilman reagent to react with, suppose, bromobenzene, for example, what we are going to get a displacement. The methyl here, which was in the Gilman, which is the nucleophile, will displace the bromine, and then we are going to end up with a methyl in here. Let me just change the color of the methyls here, just to show you what we are exactly doing. So here, CH3, here, CH3. Oops, just using different color. And then here, CH3. Do you follow me? That's actually how we do the elongation of the carbon skeleton, or one method for making elongation of the carbon skeleton is the use of Gilman reagent, reaction of Gilman reagent with any alkyl halides. As you can see here, this is aryl halide. Aryl halide works nicely. Alkyl halides works nicely. Vinyl halides works nicely. That's actually the point for this reaction. For example, again here, the easiest reaction here, just how to start from, let's say, okay, let me just show this. How you could prepare we just use different color. It's all right. Instead of this, it's just yeah. Okay, fine. Okay. Suppose we want to do this conversion, starting from whatever. Well, it's okay. How to prepare such a compound? If you're starting from any alkane, any corresponding cycloalkane. If you think of it, then definitely you can think of it as this green type here, this green alkyl chain, to be Gilman, for example here. This one, when we allow it to react twice, when we prepare it with copper lithium, if we allow this to react with a corresponding one, this one to be alkyl halide, for example, Br, if we mix these together, then definitely we are going to get that, isn't it? Is that true or not? Is there any question about it so far? Any question? I'm waiting your response, guys. Okay, now, if we mix these together, then definitely that will go there. Now, how to prepare this? I think you could think of it in a reverse way. This Gilman definitely can be prepared from the corresponding lithium compound. So, sorry, just drawing it in a correct way. The lithium here compound can be prepared from the corresponding halogen. This halogen again can be prepared from halogenation of the corresponding cyclopentane in the presence of light, for example. Now here, this one is the easiest one. We can only prepare it from, directly we can prepare it from the corresponding cyclobutane in the presence of Br2 and light, for example. So by this way you can see we could prepare and make elongation of the carbon skeleton. Now there is a new reaction has been discovered very recently, which is called the Suzuki-Bayero reaction. You may read it at home. We will not include it in the final exam in order not to, to make the material too elongated and too much for you. So section 10.5, from Suzuki reaction and to the end of the chapter, it will not be covered in the exam. So it's just for your own reading. With that, actually, we will be done with this chapter, and next week, inshallah, we will start with a new chapter, which is chapter 11. Clear so far? Is there any question, guys? All right. Okay. Thank you very much for your attendance, and inshallah, wait from me from now until tomorrow to make a decision regarding the final exam and the nature of the final exam. I wish you all the best, and see you inshallah very soon. يعطيكم العافية. السلام عليكم.